So we want to actually be able to do things with distributions. We certainly want to be able to plug them into linear, at least linear, but in fact linear is really where the heart of this theory works. Linear differential equations. So we need to be able to add, subtract, multiply. Well, multiply them by each other, maybe not. We'll see, that's kind of interesting. And certainly differentiate. And the way we're going to find out the definitions and figure out some properties of that is always going back to the model of thinking of a function as a distribution by integrating against a test function. Okay, so I hope when you look at this handout that it's fairly easy, especially maybe once you get a hint on the first one, just to get you into the mode of making these definitions. So we want to know how to define how to multiply a distribution by a number and add two distributions. Well, we're going to see what happens to functions when we think of them as distributions. So this is number 1. This is 1a. And it's linear. And the interesting thing is that we've used already the fact that this is linear in the phi variable to justify the requirement that any distribution should be linear in how it acts on test functions. But now we are taking advantage of the fact that this is also linear in the f argument. Very basic properties of integrals. Remember, this is integral from minus infinity to infinity. I'm just not writing it. Try to make my g's and ph's distinct. Okay. All right, so that's just a times what f does to phi plus b times what g does to phi. Okay. So to make this kind of thing, this kind of observation into a definition, this is a real theorem about how functions work. To make it into a definition of distributions, just ignore all that stuff and change the f to a u and the g to a v and say there's my definition of what it does for distributions. Any distribution, its job is to eat test functions. V eats test functions. This is a perfectly well-defined number, and then this is going to be the definition of that distribution. One thing I should have gotten you to verify, although maybe I'll do this later when we really tidy up and have the very precise definition, we should verify that this new gadget, well, what did we, so far all we've really know to require is that it yet again be linear in the phi variable. That's really easy, but good thing to do right now if you want, and if you, especially if you think if it's a little confusing. Basically what we've got, remember, is we've got this space of test functions. To be a little bit more formal about this, and what we're saying is that a distribution, is a linear transformation from this vector space to this very simple vector space. And this is the definition of how you add linear transformations, ever, always. And it's a very easy thing to show that when you add linear transformations or scalar multiply them, you get linear transformation. So that's the general context here. And then, so for example, what about one of the few distributions we know that isn't so far that we know? We'll know more by the end of this handout. But so far, we just know like the delta A's. What is this acting on phi? Well, by definition, then, it's just 3 times delta minus 4 of phi plus 7 delta 5 acting on phi. And we know what, by definition, what those are. That just takes phi and evaluates at minus 4, and that just takes phi and evaluates it at 5. The picture is really more important. Delta minus 4 is a delta function here, and then I triple it in size. And then delta 5 is a unit delta function here, and then I septuple it in size. And it's really the sum of those two spikes. If you then integrate that against a test function, it ends up just picking out 3 times the value here and 7 times the value here. But these pictures are very useful, and they're not totally misleading. Remember, this should be, and this is another good thing that you could prove if you want another exercise, that's the limit of an honest-to-God spike at minus 4 plus an honest-to-God spike at 5. Make sure that the area here is 7, the area here is 3, and then squish this down and squish this down while keeping the areas constant. The limit of that should be this distribution. The cool thing is we're getting beyond having to do that every time by just using these formal ideas of pairing the distributions with a test function input. That's some of the formal power of the theory. Okay, so now the second thing we could do which actually gets us into tricky terrain already pretty quickly. But we might as well do it right now, or at least start it right now. Multiplication by a function. You can definitely multiply functions by each other, and here we really have an asymmetry. We're not going to define how to multiply two distributions, because in fact it's really tricky and sometimes just downright impossible. But let's take some function psi, and it's a big hint that I'm using a Greek letter for that, and multiply that by some halfway decent function, the kinds of functions we've been talking about as the physical functions, so it's integrable in some fairly weak sense. What does that look like when I pair it with a test function? Okay, again, by definition, it's just psi of x, f of x, that's the thing we're trying to analyze, paired with phi. Well, a little commutative, I guess I could put parentheses here to emphasize that's where they came from. Little commutative and associative laws says, okay, I compare that psi with a phi. Okay, and that's exactly of the form f eating psi phi. And because I've gotten it in terms of the original function, thought of as a distribution, eating something new, I can then just, again, erase all this stuff and change this to a u. But the tricky thing here is that this, and now we're already on to part B, okay, this, well, almost on to part B, this better be a test function. So, because we know that at the very least the fees should be continuous, we want something where we don't mess that up by multiplying by psi. So, the only simple way to guarantee that is that require that psi be continuous. And pretty soon, by the end of this handout, we're going to up the requirements for test functions. Luckily, we're also going to actually stop upping them at the end of this handout. We're going to find out, we're going to get to an equilibrium where we really actually have the correct requirements on test functions. We're actually fairly close. And that's going to require more about psi as well. But an important thing is, remember that phi is compactly supported. It vanishes outside a finitely long interval. And that cannot possibly be screwed up by multiplying by psi. No matter how weird it is, no matter how much it grows at infinity, this guy is 0 at infinity, and anywhere near infinity. And therefore, that's going to be okay. So that's not going to be an issue with psi. So no, and that's important, no support condition. We saw already with convolutions that this is all about pairing stuff together. Convolutions was pairing two functions as the convolution of those two functions. Here it's about pairing a function with a function or a distribution with a function. Support conditions are essential, or some sort of vanishing infinity condition is essential, but usually only on one thing in the pair. One of the elements of the pair. Somebody's got to bring something to the table in terms of making the pair vanish at infinity, but it doesn't have to be both of them. So there's our definition of how to multiply a distribution by a function. You just push that function onto the test function. And we'll see how that works in practice. It's probably kind of formal at this point. Okay. So number 3, would it make sense? So I wanted to just very briefly introduce you to the idea of why we would think like multiplying two distributions wouldn't work. And this is the only example pretty much of a non-function distribution that we have. Why shouldn't I be able to multiply delta times a delta, for example? Well, that guy acting on phi, okay, well, by the definition I just did, if I pretended that was a function, it'd be something like, put big question marks here, because this isn't really right. Delta on delta phi, maybe? Well, that is not a test function, but let's use sort of the physicist notation to kind of really sort of pretend it is, and we'll get a vague idea of what's happening. Okay, so I'm pretending that this thing is a function, and I'm using this delta in its guise as the delta distribution, and so that guy is just supposed to just evaluate this at 0. Okay, but this is some real number. Phi of 0 is some real number, probably not 0. And the only meaningful thing you could ever assign to this, if you had to, is infinity. So that's going to be infinity, right? I'm not saying this is the correct answer. I'm saying that this suggests why there's a serious problem of delta times delta. because delta times delta makes you want to evaluate the delta function. And that's the one thing you can't really do with delta at 0. You're not supposed to evaluate it. That's the whole point of distributions, is to not do that. Okay. So we'll come back to issues of multiplying distributions. They're really fundamental. You can do it sometimes, but with great care. The delta squared thing actually sort of shows up in quantum field theory and is one way to think about why infinities come into quantum field theory, as it turns out. But that's way beyond what we want to talk about right now. Okay, so that's kind of the warm-up stuff. The real pièce de la résistance is the differentiation, but we'll do that in the next video.